Okay, so I'm going to just take you through the complete solution of one of the recent exam problems on time-dependent perturbation theory so you can see how everything works out. And so the problem is you want to consider a Hamiltonian, which is it's a harmonic oscillator, but you see that the coefficient in front of x squared, it changes with time. And so there's a constant piece, and then there's also this time-dependent piece. And if we look at that function, it's a function that is 0 for t equals minus or plus infinity, and then it becomes non-zero in the middle. And so what we're told is that at time equals minus infinity, the system starts in the ground state of the Hamiltonian at that time. Okay, and so the Hamiltonian at that time has just k of t equals m omega 0 squared. And so then it's just the ordinary harmonic oscillator Hamiltonian with frequency omega 0. Okay, and so our ground state at that time is just the usual 0 state for the harmonic oscillator. And then it says for small values of the parameter k, so that's indicating that we're going to be okay using perturbation theory, estimate the probability that the system will have made a transition to some other state by time t equals infinity. Okay, so what we're going to do is think about just the probability of going from the state 0 to some general other state n. And what we can do is figure out what that probability is and then add up all the probabilities for the states n equals 1, 2, 3, all the way up to infinity. But actually we'll see that in the approximation of first order perturbation theory, there's not going to be very many states that we can actually make a transition to. So we look at our formula sheet to remember the formula for transition probabilities. And I've already written that down here for us. So what we need to do is just figure out what are all the things in this formula for this question. And so what we have is, number one, what are the limits of integration? And so in this case, our Hamiltonian, it's just on for all time. It's sort of the harmonic oscillator, but then this piece right here, that increases from 0 and then decreases back to 0. And so actually our time is running from minus infinity, and the question asks, what is the probability that it will make a transition to some other state just by time equals infinity? And so what we want is t0 is minus infinity in this case, and t is plus infinity. Okay, so in other questions, maybe the perturbation will only turn on at some time like time 0, and maybe it'll ask you what is the probability at some specific time like t equals 4 seconds. Okay, and then we would have different bounds for that integral. The next thing we have to figure out is what is this omega BA in our integral. And so that guy, if you remember, that is the energy difference between our final state and our initial state divided by h bar. And so since we're taking our final state to be psi b equals n and our initial state to be psi a equals 0, we know that for a harmonic oscillator, then the ground state energy is h bar omega 0 over 2, and the energy of the state n is h bar omega 0 times n plus 1/2. And the difference between those two energies is just going to be n h bar omega 0 and then n plus 1/2 minus 1/2, and then we're dividing all of that by h bar. And so that just gives us n times omega 0. So that's our omega BA in the exponent there. So omega BA is just n times omega 0. And then finally, we need to understand what is h prime BA. So h prime BA of t, this is some function of time that we get by evaluating the matrix element of our perturbation between the initial state and the final state. And in this case, we're taking our final state to be the end state and the initial state to be the 0 state. And now our perturbation is actually just going to be coming from this second term here, plugging that into the second term in the Hamiltonian there. Okay, so our h prime of t, the time-dependent term, is 1/2, and then this constant k over 1 plus t over t0 squared, and then times the x squared operator. And so that's what we want to put into our matrix element. And so the only operator there is the x squared operator. So I'll just put that in there, x squared and 0, and then we multiply the whole thing by 1/2 k over 1 plus t over t0 squared. So the quantum mechanics calculation we have to do here is just the standard matrix element of the x squared operator between two different states of the harmonic oscillator. And so what we can say is that, as usual, we'll write x equals square root of h bar over 2m omega a plus a dagger. And so n x squared 0 is going to be equal to h bar over 2m omega, and then n a plus a dagger, a plus a dagger 0. And the only state for which that's non-zero, the only other state other than n equals 0, which we don't want to talk about because we want to understand the probability for transitioning to some other state. So it's only going to be the n equals 2 state where this doesn't vanish. So acting with two creation operators on the state 0, we'll get to the state 2. And so in that case, what we find is that, so gives the non-zero result for n not equals 0. And so in that case, what we find is that 2h prime 0, just plugging everything in, it's h bar over 2m omega, and then we get this extra factor of 2, so h bar over 4m omega, and then we get this factor here, k over 1 plus t over t0 squared. And then calculating that matrix element, we just use the usual things. A dagger acting on 0 is 1, and a dagger acting on that is the square root of 2 times 2. And so we get this, finally, this factor of the square root of 2. Okay. And okay, so let's have a look. We're going to use our expression here. We've understood the limits of integration. We've understood that omega BA is equal to n omega 0, and we've understood that h prime BA is going to be this expression right here. And so now we can just plug everything in and try to do the integral. And so what we find is that p2 t equals infinity. So the p that we have made a transition, it's just the probability that we've gone to the state 2 by time equals infinity. And that's equal to 1 over h bar squared. So I'm just going to now plug everything in. So we get the 1 over h bar squared, and then we get some constants that are all squared. So 2h bar squared k squared over 16 m squared omega squared. And then we have our actual integral, minus infinity to infinity dt e to the 2I omega t. So we're setting n equals 2 here because it's only the state n equals 2 that we're making a transition to. And finally, we've got this function 1 plus t over t0 squared, and then all that is squared. Okay. And so we have to do an integral here. And fortunately, we have this formula provided for us on the formula sheet, so we could just make use of that in order to do the integral. And so that requires, just to make use of that formula, we'll want to do the substitution, maybe set x equals, or let's not use x, let's set s equals t over t0. If we make that substitution, then our integral turns into exactly the form of the integral that is provided on the formula sheet. And working everything out, we get k squared over 8m squared omega squared, and then we get t0 squared pi squared e to the minus 4 omega t0. And so that's going to be our answer. So that was basically part A of the question. Part B of this question asks, when is this going to be reliable? So we used first order perturbation theory here. It's not the exact answer for this transition probability. It's going to be, we say it's a good approximation if the perturbation is small. How do we know if it's small? Well, one easy way is just to demand that the probability itself is much less than 1. Okay. So if we have a larger perturbation, then and we find that there's a significant probability that we've made a transition, then that's where we have to worry that our approximation of first order perturbation theory is not very good. But if the p that we calculate is, say, much, much less than 1, then that sounds like this perturbation is really just a small effect. It's only having, it's only giving us a small probability that we've actually made a transition. Okay, and so that was the question.